Hello everyone, myself is Rajender, chemistry faculty. Today we will discuss about one of the important inorganic part, which is S block elements. S block elements has important role in our day-to-day life. So what are the S block elements? What are their general properties and chemical properties, and also what are the important compounds of individual elements? We will discuss today. First of all, if we see the general diagram for modern periodic table, this is the rough diagram for modern periodic table. In this periodic table, what is the placement of S block elements we have to see now. So the S block elements are placed at left hand side of the periodic table. The right side of the periodic table are P block elements, and the D block elements are sandwiched between S and P block elements. F block elements are placed at the bottom of the periodic table. So broadly, the total periodic table divided into 4 blocks. One is S block, D block, P block and F block. So this is about the placement of that 4 types of blocks in the periodic table. The total periodic table divided into 4 blocks based on the last electron. If the last electron entered into S subshell, then those all elements are placed in S block. Similarly, if the last electron entered into P subshell, then those all elements are placed in P block. And also, if the last electron entered into D subshell, then those all elements are placed in D block. If the last electron entered into F subshell, then those all elements are placed in F block. So these S block elements are very important to us because they have so much importance in our day-to-day life. Because for example, if we see one of the S block elements, sodium, potassium, calcium, they are very neat in our day-to-day life. So that here we have to discuss about their properties, we have to discuss about their important compounds, their preparation and their properties. One of the important compound of sodium is sodium chloride. It is the very important compound in our day-to-day life. Similarly, we have potassium chloride, we have calcium hydroxide, we have magnesium hydroxide. Like that, we have so many important compounds we will use those compounds in our day-to-day life. That's what we have to discuss about these S block elements in a particular manner. So let me have some discussion with you about these S block elements. So that is about the placement of S block elements. S block elements are placed at the left hand side of the periodic table. Now see, what is the definition of these S block elements? What is the classification of the S block elements? We will see now. The elements in which outermost electron or last electron enters into S subshell are called S block elements. The S subshell may have only 2 electrons in it. Based on the number of electrons present in S subshell, these S block elements are divided into 2 groups. So this classification based on number of electrons present in S subshell. The maximum number of electrons present in S subshell are 2. That's what we are dividing these S block elements into 2 groups. In that, the first group is 1A group and the another group is second A group. This first A group elements are called alkali metals, and the second A group elements are called alkaline earth metals. Why we are calling these elements as alkali metals? Why we are calling this second A group elements as alkaline earth metals is a question. So let me have some discussion with you. What are alkali metals means? The elements of 1A group are the oxides of first A group elements. When they contact with water, they vigorously form hydroxides, which are strong bases in the nature. Elements of 1A group are oxides of these 1A group elements. When they react with water, when they contact with water, vigorously they form hydroxides, which are strong bases in the nature. And also these are called alkalis. For example, here we will see the metal M of first A group reacting with water, they form MOH type of hydroxides with liberating water. While we are balancing this, we require two coefficient before H2O, 2 MOH, 2 M. This is the balanced equation for the formation of hydroxide when metal react with water. Whenever the oxides of 1A group elements, the general formula of oxides of 1A group elements will be 3, but one here I am taking the monoxides. The common formula of monoxides is M2O. When they contact with water, they form again MOH type of hydroxides like this. These hydroxides are strong bases and these are also called alkalis. What is the meaning of alkali? Here is the substances which produces OH minus ions in presence of water are called alkalis. Alkalis are bases, but all bases are not alkalis. Here this is the very important statement. When these MOH type of hydroxides dissociate into M plus plus OH minus, as they are producing OH minus ions, these MOH type of hydroxides are called alkalis, and these are strong bases. That's what these alkali metals, these first A group elements are called alkali metals. Moreover, second A group elements are called alkaline earth metals. These are also produces hydroxides which are strong bases, and they can also produce as OH minus ions. But the hydroxides of these second A group elements are more available in the earth's crust. That's what we call these second A group elements as alkaline earth metals. For example, here we will see the M is the metal, stands for second A group element. So when second A group element react with water, they produces MOH taken to type of hydroxides with liberation of hydrogen gas. Here we will see 2 moles of H2O. Or the MO type of oxides will be formed by this second A group elements. When these react with water, they can produce as MOH taken to type of hydroxides. These hydroxides, when ionized into ions, they produce as M plus 2 type of ion with liberation of 2 moles of OH minus ions. These hydroxides also producing OH minus ions. That's why these are called alkaline, but these are earth metals, nothing but the hydroxides of these second A group elements are more available in the earth crust. That's what we will call these elements as alkaline earth metals. This is the common name for this first A group elements. And what is the general configuration of these first A group elements? What is the general configuration of this second A group elements? We will see now. In S subshell, the maximum number of electrons are 2. Whenever the S subshell is with 1 electron, then those all elements are placed in 1A group elements, and when the S subshell is with 2 electrons, then those elements all are placed in second A group elements. So the common configuration of this first A group elements can be write in the form of NS1 and for this NS2. For S block elements, the common configuration will be Ns to the power of x. Here the x we will take 1 or 2 as we have only 2 electrons in S subshell. This is about the classification of S block elements. S block elements are divided into 2 groups based on the number of electrons present in S subshell. S subshell maximum consisting 2 electrons. That's why we will divide this S block into 2 groups. One is first A group and second A group. These first A group elements are called alkali metals as they are producing hydroxides when they contact with water, and these are also called alkalis. Alkali is the base which can produces OH minus ion. Alkalis are bases, but all bases are not alkalis. For example, take ammonia. Ammonia shows basic nature, but it is unavailable to produce OH minus ion. So this is about the classification of S block elements. Next, here we will discuss about first A group elements first, then after we will go for second A group elements. First A group elements are also called alkali metals. What are the elements under this category, under this group are? Number 1, lithium, sodium, potassium, rubidium, cesium, francium. These are the elements placed in first A group. Here we have hydrogen also at the top of these group elements, but we should not include this hydrogen in this first A group because hydrogen shows similar characters with this first A group elements, as well as it shows some abnormal properties, different properties with this first A group elements. As it is exhibiting similar properties with first A group, also this hydrogen express the similar properties with seventh A group elements also. So that the hydrogen place is the topic of discussion. Hydrogen place till now not decided properly because of hydrogen exhibiting similar properties with this alkali metals, also expressing with seventh A group elements. What are the seventh A group elements? Fluorine, chlorine, bromine, iodine, astatine. These are the elements in seventh A group elements. For example, if we see the similar properties of hydrogen with this first A group elements, hydrogen configuration, atomic number is 1, it is with 1s1. The common configuration of alkali metals is NS1. With respective to configuration, the hydrogen resembles alkali metals. Then what is the different property of hydrogen with these elements is, hydrogen is a non-metal, but the elements placed in first A group are metals. So different property it is. What is the similar property of hydrogen with this seventh A group elements is, all seventh A group elements are diatomic molecules. Diatomic molecules means they have X2 type of molecules. Hydrogen also can exist in the form of H2. Like that, hydrogen is exhibiting similar properties with seventh A group. Seventh A group elements are diatomic molecules, hydrogen also. Seventh A group elements are non-metal, hydrogen also. As the hydrogen is exhibiting similar properties with first A group as well as seventh A group elements, we cannot include this hydrogen either in first A group or in seventh A group. That's what the place of hydrogen in the periodic table is a topic of discussion. So that we should not include that hydrogen in the first A group elements as well as in 7th A group elements. So what are the first A group elements here? These are the elements placed in first A group elements. We will discuss this topic by dividing into three main parts. One part is general and physical properties of first A group elements, chemical properties of first A group elements, important compounds of individual elements of this first A group. We will divide this topic into three parts: general and physical properties, chemical properties, and compounds of individual elements. Here we have the compounds of sodium, sodium chloride, sodium hydroxide, sodium carbonate, sodium hydrogen carbonate. If you see this potassium, potassium carbonate, potassium hydroxide, potassium chloride, like that we have some important compounds for potassium. And this sodium potassium shows biological importance also. What is the biological importance of this sodium and potassium also we will discuss in this topic. So let me go through the first part of this alkali metals, which is general and physical properties of alkali metals. So let me take the general and physical properties of alkali metals. Here I will start the properties of these alkali metals from their electronic configuration, because the total properties of all these elements will be based on electronic configuration only. That's why it is very important property. If we want to know about the electronic configuration of this first A group elements, we need to write about their atomic numbers. The atomic number of lithium is 3. The differentiation between this lithium and sodium is 8, so that here we have 11 is the atomic number of sodium, and the differentiation is 8, so 19. Here the differentiation is 18, so the atomic number of rubidium is 37, and here the differentiation is 18, so 55, and differentiation is 32, so atomic number is 87. This is about the atomic numbers of this first A group elements. Before we are going to electronic configuration of these elements, let me have some discussion with you about the noble gases. The noble gases are helium, neon, argon, krypton, xenon, radon. Their atomic numbers are 2, 10, 18, 36, 54, 86. These are the atomic numbers, and these are also show some electronic configuration. While we are writing the configurations of this first A group elements, we need to know about the atomic numbers and configuration of these noble gases. So the configuration of this lithium is 1s2 2s1, as it has only 3 electrons, and the sodium is 1s2 2s2 2p6 3s1. Next, potassium is 1s2 2s2 2p6 3s2 3p6 4s1. For rubidium, it may have some difficulty to write about the configuration of rubidium because it has some more large. So instead of this 1s2, simply we can write the helium, which shows 1s2 configuration. So instead of this 1s2, here I can write the configuration of helium like this. So lithium is with helium 2s1, sodium is with this 1s2 2s2 2p6 resembles the configuration of neon, and potassium up to this 18 we can write the configuration for argon. Simply for rubidium, after the argon we have krypton, so configuration of rubidium will be krypton 5s1. Next, for cesium, up to xenon 54 is there, so xenon it can be 6s1. Next, for francium it will be radon 7s1. By seeing the configurations of all these first A group elements, The general configuration of these alkali metals can be written in the form of noble gas configuration with NS1. If you see lithium, instead of this 1s2 we can write helium. If you see sodium, instead of this 1s2 2s2 2p6 you can write neon. So similarly for all these elements, they are with one excess electron compared with their nearest stable configurations. The nearest stable configuration for lithium is helium. It is with one excess electron in which 2s orbital or 2s subshell. So this is about the general configuration, which is with the noble gas. NS1 is the general configuration of this first A group elements. Next property of this group elements is general property atomic and ionic radius. Atomic radius and ionic radius. This is very important property which decides the all other properties. So for example, if you see lithium, sodium, potassium, rubidium, cesium, francium, in this the francium is radioactive element. Francium is radioactive element. So lithium is with 1s2 2s1. Sodium is with 1s2 2s2 2p6 3s1. The last shell configurations for all these elements is 2s1 3s1 4s1 5s1 6s1 7s1. The last shell configurations, the number of shells, after seeing this configuration we can conclude that the number of shells are increases on moving from top to bottom. With increase in the number of shells, the size will be increases. For sodium, the size increases from lithium to sodium, as well as for potassium the size will be increases, for rubidium increases, for cesium increases. Finally the cesium is with large size. On moving from top to bottom, the last electron is entered into different shells so that the number of shells are increases. With increase in the number of shells, the atomic size of this group elements is increases on moving from top to bottom. If you see here, left position, right position, this is the left position of periodic table, right position of periodic table. On moving from left to right, the atomic radius will be decreases. On moving from top to bottom, the atomic size will be increases. Here radius will be increases, number of shells increases, so the size will be increases. Here to here, atomic radius or atomic size will be decreases because effective nucleus charge will be increases, that's why size will be decreases. So atomic radius not only of these first A group elements, in a group from top to bottom the atomic size will be increases. This is because the upcoming electron, the last electron, the outermost electron entered into different shells. That's why number of shells increases, so size will be increases. This is about the atomic radius or atomic size. Next, ionic radius. The first A group elements, as they have one electron excess than their nearest stable configurations, they involves in the loss of only one electron which is present in last subshell or last shell. When they involves in the loss of one electron, for example, M can be taken as alkali metal. When it involves in the loss of one electron, it forms M plus 1 type of ion. This M plus 1 type of ion is also called unipositive ion. For this unipositive ion, we need to discuss about the size variation from top to bottom. So lithium can be exist in the form of lithium plus 1, sodium can be exist in the form of sodium plus 1, all respective elements can form their unipositive ions like this. The size variation of this unipositive ions we have to discuss now. So, atomic size increases gradually from top to bottom because number of shells are increases. Here their unipositive ions, the sizes of unipositive ions also gradually increases from top to bottom. So, here M is in gaseous phase, M plus 1 is in gaseous phase. The sizes of unipositive ions in gaseous phase gradually increases from top to bottom like atomic size. So, what is the statement here? Atomic size and ionic size, or atomic radius and ionic radius gradually increases from top to bottom in first A group elements. This is the size variation when they are in gaseous phase. The size variation when they are in hydrated phase will be different compared to this gaseous phase. So, what is the hydrated radius? Very important. Hydrated radius. So, before we are going to this hydrated radius, let us have some small discussion about the hydration. What is the hydration? Means when 1 gram mole of gaseous ion dissolved in water, that ion is called hydrated ion. So, what is the expression for it? This is the unipositive ion which is in gaseous phase of alkali metal. When it dissolved in water, the resultant ion is in hydrated phase, is nothing but aqueous phase. So, this ion is called hydrated ion. We need to remember here the size variation of unipositive ions is increases from top to bottom, but the size variation of hydrated ions of 1A group elements is different from our expectations. So, what is that different order which we are following for this hydrated ions is the topic to discuss now. So, let me take the lithium plus 1 ion which is in gaseous phase. When it dissolves in water, it forms lithium plus 1 aqueous. This process is called hydration. This process is called hydration. When 1 gram mole of this lithium plus 1 ion dissolved in water, with this aqueous lithium plus 1 ion, we will get some energy. That energy is called hydration energy. And the resultant ion is called hydrated ion. From lithium plus 1 to cesium plus 1, when they are in gaseous phase, the size is increases. This is the topic just now we have discussed. We need to discuss about their size variation of the hydrated ions. For the hydrated ions, due to very small size of lithium plus 1 ion, the more number of water molecules will be attracted towards this small sized lithium plus 1 ion. As a result, the size of hydrated lithium plus 1 ion is more compared to other hydrated ions in the alkali metals. For example, if you take sodium plus 1 which is in gaseous phase, when they dissolves in water, it also produces Na plus 1 aqueous form. So, size variation here I will see, this is the lithium plus 1 ion, consider which is in gaseous phase. So, lithium plus 1 ion attracts more number of water molecules towards itself, because water is the polar solvent. When we see the general diagram, means the general structure of the water, oxygen is more electronegative element than hydrogen, so the polar covalent bond will be move somewhat towards this oxygen, as you have partial negative charge on the oxygen and hydrogen is with partial positive charge. Like that, 6 water molecules are surrounded the one lithium plus ion like this. Partial negative oxygen, partial negative oxygen. Here also we have partial negative oxygen and hydrogen is with partial positive charge. So the attractive force which works between this lithium plus 1 and this partial negative charged oxygen is ion dipole force. This force is called what? Ion dipole force. Due to this ion dipole force, the water molecules are attracting towards this lithium plus 1 ion like this, so that the hydrated radius of lithium plus 1 is with like this. This is the hydrated radius of lithium plus 1 ion. From lithium plus 1 to Na plus 1, when they are in gaseous phase, the size will be increases. So when size increases of this gaseous phased ion, the hydrated radius of the resultant ion will be decreases. So like this, Na plus 1 is with this much size, and this H2O may have very less capacity to attract the water molecules towards itself. That's what the hydrated radius from lithium plus 1 to Na plus 1 will be decreases. The size variation for unipositive ions of gaseous phase will be increases. So the order will be lithium plus 1 less than Na plus 1. So finally the Cs plus 1 is with large size. But for this hydrated radius, due to increase in the ionic size in gaseous phase, the hydrated radius of the resultant ions will be decreases. This decrease in the hydrated radius of unipositive ions results decrease in the ionic mobility of their ions in the solution phase or in the water. We will see the ionic mobility of these hydrated ions when they dissolved in water. Generally, the salts of alkali metals shows electrical conductivity due to free movement of ions, because those salts are producing ions in the water when they dissolved in it. But the hydrated radius of the resultant ions will be decreases. When the hydrated radius decreases, the ionic mobility of the ions will be increases. So conductivity of the resultant salts will be increases on moving from top to bottom, because of hydrated radius will be decreases. When hydrated radius decreases, smaller the ion can move very freely in the water. If the size of ion is more, it has some difficulty. Larger sized ion can move very slowly, smaller sized ion can move very fast. Means the conductivity of the salts of alkali metals in the water will be increases on moving from top to bottom. This is about atomic radius, ionic radius and hydrated radius. Next property, ionization energy. They have one electron in their outermost shells. When they involve in the loss of that one electron, they form unipositive ions like this. M, which is in gaseous phase, plus energy gives M plus 1 which is in gaseous phase, plus they involves in the loss of one electron. For example, take sodium, the configuration is 2, 8, 1. It required the energy which is called first ionization energy. So that the sodium ion is formed with the configuration 2, 8. This configuration is called noble gas configuration. This is similar to neon configuration because the neon is the nearest stable configuration, nearest noble gas to this sodium. Also it releases one electron. The energy required to remove one electron from neutral isolated gaseous atom is called first ionization energy, IE1. If we want to remove one more electron from this unipositive ion, the required energy is called IE2. The required energy is called IE2. While we are removing the electron from unipositive ion of sodium, we need to remove the electron from stable noble gas configuration. So it is highly difficult. It required very high energy as you remove the electron from stable configuration. That's why the second ionization energy is extremely high compared to first ionization energy. Here we will write like this: IE2 is greater than IE1. This is about the ionization energy. Variation of ionization energy in a group from top to bottom we have to discuss. The ionization energy is the periodic property which will depends upon the atomic radius. And here we have discussed just now, the atomic radius from top to bottom increases due to increase in the number of shells. When the atomic radius or atomic size increases gradually, the distance between the nucleus and outermost electron will be increases. In cesium, the outermost electron is loosely binded with the nucleus of cesium. That's what the required energy to remove this electron from outermost shell will be very easy compared to the lithium. So that here the relationship we will follow, what is the atomic size increases because number of shells are increases. With increase in the atomic size, nuclear outermost electron distance will be decreases, so that ionization energy will be decreases. So what is the relation between these two properties? Means ionization energy is inversely proportional to atomic size. Due to low ionization energy and large atomic size, the element cesium shows more photoelectric effect. The element which shows highest photoelectric effect in this first year group elements is only cesium. So why it is exhibiting that maximum photoelectric effect means because it has larger atomic size and lower ionization energy. What is the photoelectric effect also the question now? When the suitable beam of light strikes on the surface of the metal, the electron will be emitted from the surface of metal. So the process of emission of electron from the surface of metal when suitable beam of light strikes on the surface is called photoelectric effect. Consider this is the surface of cesium. This is the beam of light striking on surface of cesium with some suitable frequency, and the electron will be emitted from the surface of metal. This process is called photoelectric effect. This will be possible when larger atomic size and lower ionization potential is there. That's what the very important property of this cesium is. Due to this maximum photoelectric effect, this cesium will be used in solar cells for photoelectric conductivity. Cesium is used in solar cells for photoelectric conductivity due to emission of electron from the surface of metal. The maximum photoelectric effect can be shown by this cesium due to its large size and low ionization potential. This is the variation of ionization potential in a group from top to bottom. Let me explain once again. Amount of energy required to remove the electron from outermost shell of a neutral isolated gaseous atom is called ionization energy or first ionization energy. If we want to remove the one more electron from resultant unipositive ion, that energy is called second ionization energy. The second ionization energy is more than the first ionization energy because size of this m plus 1 is lesser than the size of m. As we have the relationship ionization energy is inversely proportional to atomic size, the size of m plus 1 is lesser than the size of m, that is why ionization energy of second ionization energy will be more compared to first ionization energy. This is the second property, ionization energy. Next, metallic character and electropositivity. Next property, metallic character and electropositivity. S block elements are placed at the left hand side of the periodic table. So every horizontal row can starts with this S block element, ends with 8th A group element. Left to right the sizes will be decreases, means the alkali metals has large sizes in their respective periods compared to other elements, because every period every horizontal row can starts with this first A group element. In the respective group the size will be increases. So metallic character, electropositivity, these two properties will depends upon the atomic size. The metallic character and electropositivity are directly proportional to atomic sizes. Every horizontal row can starts with first A group element, ends with 8th A group element. These elements are with large sizes in their respective horizontal rows. Due to their large sizes, they shows more metallic character and more electropositivity in the respective periods. If we see that respective group on moving from top to bottom, size is increases because number of shells increases. With increase in the size, metallic character and electropositivity both will be increases. So cesium is with more electropositive in nature compared to lithium. This is another property, metallic character and electropositivity. This electropositivity and large atomic size, low ionization potential will decides the reactivity of these first A group elements. Reactivity of alkali metals. Alkali metals are highly reactive metals. These are highly reactive metals. They react with water vigorously. Even when we expose these alkali metals to atmosphere, immediately they contact with the moisture present in the atmosphere or the oxygen. It affects the chemical activity of oxygen, so immediately they can form their some compounds. What is the reason to get this highly reactive nature of these alkali metals? They have large atomic size, one of the reason is large atomic size, and the another reason is low ionization potential. Due to this low ionization potential, they involves in the loss of electron very easily. Large atomic size, low ionization potential, and high electropositive elements. Due to these three reasons, these alkali metals are highly reactive metals. What is the variation of reactivity in the respective group is the question now. Throughout the alkali metals are highly reactive metals due to these three reasons. But what is the variation of reactivity of alkali metals in the respective group? Means from lithium to cesium, atomic size increases, ionization potential decreases, electropositivity, tendency to lose the electron from outermost shell is increases. These are the suitable properties which we require to get the high reactivity. So cesium follows these properties strictly. Means cesium is with large atomic size, it is with low ionization potential, this cesium is with high electropositivity. So that the reactivity of this first A group elements increases from top to bottom. Reactivity increases from top to bottom. When they react with some other reactants, mostly they form, maximum they can form ionic compounds which are colorless compounds. So M is the alkali metal. When it forms the reactant, another reactant like X, it forms the compounds which are called ionic compounds, in which the M is with M plus 1, because we have discussed already, they have one electron excess than their nearest stable configurations. That's what they can form unipositive ions. Those unipositive ions exist in ionic compounds in M plus 1 form. These ionic compounds are colorless compounds. This is about the reactivity variation, metallic character and electropositivity. Metallic character and electropositivity is directly proportional to atomic size. Atomic size gradually increases, so metallic character and electropositivity both will be increases. The elements which are placed at left hand side are with large sizes, more electropositivity, low ionization potential. Due to the three properties, they are highly reactive metals. So to avoid that reactivity, to get those elements in their elementary state, we will store these alkali metals in kerosene or in any organic liquid. When they are stored in any one organic liquid, we will avoid the contact of these elements with the atmosphere. As we are avoiding the contact between these alkali metals and atmosphere, we will reduce the chemical activity of these alkali metals. So that is about the reactivity, which is very important property of these alkali metals. Next, see, we are in general and physical properties of alkali metals. 1A group elements are broadly divided into three parts. For our convenience, here we are dividing that 1A group elements into three parts. One is the general and physical properties. Here we are in the discussion of general and physical properties of alkali metals. After the properties of all these alkali metals, we will go through on the next part, chemical properties. Here we need to remember one thing, we should not by heart the values of these alkali metals, but the variation is important, because the questions are based on, means the question will be on variation of these properties only, not based on the values. So students, you should not by heart the values, just you need to remember the variation of these properties. So next property is melting point and boiling point. Melting point, boiling point depends on cohesive forces. Cohesive forces are helpful to bind the atoms in metallic crystal. What are the cohesive forces? These are the forces which are helpful to bind the atoms in metallic crystal. Here the statement for this alkali metals is, the statement for the melting point and boiling point of this alkali metals is, these metals are with low MP-BP values compared to other metals. Or the another statement here is, these metals are soft in nature, means even we can cut with knife also, that much softness is there for these metals. So what is the reason for these two statements? Here I will give the explanation to you. Melting point, boiling point depends on cohesive forces. These cohesive forces are the forces helpful to bind the atoms in metallic crystal. For example, let me take the metallic crystal like this. These are the atoms of one respective metal present in the crystal. These alkali metals are with the general configuration noble gas with NS1, means they have one electron in their outermost shell. So for example, if we see the lithium plus 1 ion after losing the electron in its metallic crystal, so that is the electron of lithium plus 1. So same lithium plus 1, here we have like this. Here is the electron, this is the lithium plus 1, that is the electron. This is the arrangement of the ions while they are involving in the metallic bond in metallic crystal. These electrons are attracted by both two lithium plus 1 ions like this. The cohesive forces depends upon the size of the metal ion in metallic crystal. Smaller the size of the ion, stronger is. This cohesive force decides the melting point and boiling point of the respective metal. If stronger is the cohesive force, the MP and BP values will be more for this respective alkali metal, because stronger force if is there, more energy is required to convert it into liquid form, which requires melting point, and to gaseous form we require from solution phase to, from liquid phase to gaseous phase we require the boiling point. The MP BP values depends on these cohesive forces. The cohesive forces, if is strong in the metallic crystal, the melting point and boiling point will be more. This cohesive force depends on the size of the metal. On moving from top to bottom, the size of the metal will be increases. This is the large sized cesium consider. The cohesive forces will be decreases with the electron here we have. So cohesive forces are decreases. With the decrease in the cohesive forces, the melting point, boiling point of these alkali metals also decreases. So on moving from top to bottom, cohesive forces will be decreases. So MP BP values are decreases. Here the statement is low MP BP values compared to other metals, means these metals are with only one outermost electron, as they have only one outermost electron, only one electron can take part in metallic bond formation. When the valency electrons are more, the stronger metallic bond will be formed, but we have no chance to get such type of stronger bond for alkali metals as they have only one outermost electron. That's why weak metallic bond is there. That weak metallic bond result in the soft nature of this alkali metals. The softness of alkali metals increases gradually on moving from top to bottom. Melting point, boiling points of this alkali metals are decreases on moving from top to bottom. This is about melting point and boiling point. The melting point, boiling point of these metals are very less compared to other metals, as only one electron is involving in the metallic bond formation, and these metals are soft in nature, means we can cut with knife also. Next property, density of these metals. Density of these metals gradually increases from top to bottom. Here these are the elements: lithium, sodium, potassium, rubidium, cesium. So on moving from top to bottom, density increases. So density D equals to mass by volume. The molar mass of these elements with increase in the atomic number. So with increase in the mass, the density of these elements also increases. According to this concept, we will expect the order like this: lithium, sodium, potassium, rubidium, cesium. So this is the order for increase in the density. But the abnormal order followed by these alkali metals respective to density. This is the expected order. We are expecting this order according to this concept, but the abnormal order is, according to our expected order, potassium is more density element or more density metal than sodium, but in the practical order, the potassium is lighter than sodium. So this is the practical order. In practical order, practically the potassium is lighter than sodium. What is the reason for it? Means lithium to sodium size increases, sodium to potassium also increases, potassium to rubidium size gradually increases. With the volume increases, the density, with the increase in the volume gradually, means size gradually, the potassium why is lighter than the sodium means due to abnormal increase in the size of potassium from sodium, the potassium is lighter than the sodium. Let me explain once again. On moving from top to bottom, molar mass of these elements is increases. So density D equals to mass upon the volume, D equals to m by V. If molar mass increases, the density also increases with increase in the atomic mass. This is the expected order based on this concept, but the practically potassium is lighter than sodium. This is because potassium is with abnormal increase in the size compared to other increase in the sizes of elements. From sodium to potassium, the size of potassium abnormally increases. That's why the density of potassium will be lesser than the sodium. This is the density. So students, once we see what are the properties till now we have discussed: atomic radius, ionic radius, hydrated radius. Atomic radius, ionic radius increases from top to bottom, but the hydrated radius will be decreases. That hydrated radius decides the ionic mobility of the ions. Larger the hydrated radius, lesser is the ionic mobility of the ions. Next, ionization potential, electropositivity, metallic character, melting points, boiling points, reactivity. Like that we have discussed general and physical properties of some elements, means alkali metals. In the next session we will discuss about the chemical properties of these elements.